Hello, in this presentation, I'd like to talk about our recent research results on simulating braking waves with the Reynolds stress turbulence model. My name is Yuzhu Per Li. I'm from Department of Mechanical Engineering at the Technical University of Denmark. To begin with, I'd like to talk about the background of the present study. In the past 2 decades, previous safety studies of braking waves have shown an obvious tendency to severely overestimate turbulence levels, both before and after braking. For example, here, Brown et al. 2016 simulated braking waves with different RSMs models. In this figure, A and B are the locations before wave braking where the turbulent kinetic energy, K, should be almost zero. However, you can see in this figure here that almost all of the Reynolds models over-predicted the turbulent kinetic energy before braking. This will lead to inaccurate prediction of braking point and also undertow velocity profiles. To solve this problem, a recent breakthrough was made by Larson and Furman 2018. They found that this problem is due to the widespread unconditional instability of seemingly all two-equation turbulence models in the potential flow core region beneath surface waves. Moreover, they derived a simple and elegant method for formally stabilizing such models and solved this long-standing problem. The marked improvement can be seen in this figure A, B, and C. A and B demonstrates that the new stabilized closure model eliminates the widespread overprediction of turbulence before braking and also in the outer surface zone just right after the wave braking start. And figure C demonstrates pronounced improvements in the averaged undertow velocity profile in the pre-braking region. However, a problem still remains to be solved. That is, even the stabilized two-equation models in Larson and Furman 2018 were still rather inaccurate in the inner surface zone. We can see here in this figure A, B, and C that before braking, this black solid line predict pretty well, match with the experimental data. And also it predicts better than the blue dashed line, which is the standard K omega model in the outer surface zone. However, in the inner surface zone, which is in figure C here, shows that none of the standard or stabilized K omega model are able to predict the undertow velocity profile well. Therefore, it simply requires yet more advanced methods of achieving turbulence closure for accurately simulating braking waves, all the way from pre-braking to the inner surface zone. Having this problem in mind, in the present study, we took Reynolds stress models as our primary candidate for simulating braking waves. Two-equation models such as K epsilon or K omega models, they are quite efficient and also simple to implement, so they are widely used in engineering practice. However, they're based on the Bosniak's assumption of eddy viscosity, assuming isotropic Reynolds stress. Therefore, one K equation can simulate all of the Reynolds components. However, Reynolds stress models, for example, LRR stress epsilon model and Wilcox stress omega model, they are simulating 6 unknowns in the Reynolds stress. Here are the 9 components in the Reynolds stress tensor, but we know this, the Reynolds stress tensor is symmetric, so that there are actually only 6 unknowns in this matrix. So the RSM models will solve 6 equations of Reynolds stress and 1 equation of epsilon or omega equation. So that the RSM models, they break from the Bosniak's assumption of eddy viscosity And with this feature in this model, we think that they can capture the physics more realistically comparing to two equation models, and they are expected to produce more accurate results for predicting breaking waves. And moreover, compared to the large eddy simulation and the direct numeric simulations, RSMs actually have much lower computational cost than LES and DNS. So here for RSM, we will present the Wilcox stress omega model for our analysis and applications. We also did the same analysis and application for the LRR stress epsilon model and achieved similar conclusions and results. But for the sake of brevity, we only present one of them. So here are two equations of Wilcox stress omega model. Well, actually, the first equation for tau is actually 6 equations because we solved 6 components of the Reynolds stress. So there would be 6 tau equations plus 1 omega equation. And it is noted that in the first equation, the fourth term in the right-hand side of the equation, buoyancy production, is added to the original Wilcox model for simulating surface waves. And here are the closure coefficients of the Wilcox stress omega model according to the original model in Wilcox books 2006. So the stability analysis here will follow the study in Larsen Furman 2018, where they proved the two equation models in terms of K omega and K epsilon are unconditionally unstable in the potential flow region beneath surface waves. Here we will perform novel analysis for the stability of RSM models. Let's continue to take the stress omega RSM model as example for the analysis. In 2D potential flow region, we neglect diffusive, convective, and cross-diffusion terms, also invoking the definition of K, assuming isotropic Reynolds stress tensor. We will result in 3 partial differential equation system consisting of a K equation, tau1, 2 equation, and an omega equation. It turns out to be convenient to utilize a utility variable psi equal to K over tau1, 2, so that K and tau1, 2 equation are combined to 1. Now we have 2 equations with one for psi, one for omega. Setting both equations above to 0, the asymptotic values of psi and omega can be found as these 2 expressions. This means regardless of their initial values, psi and omega will eventually evolve to a constant such that the partial differential equation partial psi over partial t and partial omega over partial t all equal to 0. And then we insert the asymptotic values back to equation system 1, especially the K equation, the asymptotic exponential growth rate of K, with definition of 1 over K times partial K over partial T, is expressed as the equation below. And if we take a look of the gamma infinity square, we can see that it's actually a constant times S12 square, because this alpha hat, beta hat, and gamma hat, also the C1, are all constants. So it actually can be expressed as gamma, which is an expression of the constant times S12. So now let's take a look at S12. For progressive waves, following the analysis in Mayer-Masson and Larsen Furman, analytic velocity fields of progressive waves can be expressed as equation of U and equation of V. And when inserting the velocity fields back to S12 and period average in S12 will yield an equation equal to 0. If we recall the asymptotic exponential growth rate of K, gamma infinity, it's an expression of a constant times S12. Since S12, after period averaging in the potential flow or waves, is 0, the tau infinity is also equal to 0 when simulating progressive waves. This implies that the Wilcox stress omega turbulence model is unconditionally stable for modeling surface waves, since there is no unphysical growth beneath surface waves of the turbulent kinetic energy. So we tested our stability analysis results by running a wave train simulation and compared it with two-equation K omega model. This shows the wave elevation along the time, and we can see that the standard K omega model started to decay for the wave elevation after 30 wave periods, while the Wilcox stress omega RSM model can maintain the wave amplitudes until 50 wave periods and further. This means the Wilcox stress omega RSM model can simulate stable wave trains because there's no unphysical growth of the turbulent kinetic energy beneath surface waves. So the present study finds that the Bosnisk assumption is actually the fundamental reason for turbulence model instability in the potential flow regions. To further investigate the performance of Reynolds stress models for simulating flows that intend production of turbulence, we simulated oscillatory wave boundary layer flows with both stress omega model and K omega model as comparison. So we reproduced the experiments of Jensen et al. 1989, which was a classic experiment performed at DTU oscillating tunnel 30 years ago. And here we presented 4 time instants in terms of omega t equal to 0, equal to 45 degrees, 90 degrees, and 135 degrees. If we see on the right side this sine curve with omega t equal to 0 degree, denoting the time instant just after near bed flow reversal, and we have omega t equal to 45 degree, means the acceleration stage, and omega t equal to 90 is at the peak free stream flow, and also omega t equal to 135 degrees at the deceleration stage. If we see these figures for mean flow velocity and turbulent kinetic energy by both K omega and stress omega models, we can see that both two models model the mean flow velocity quite well compared to experiments. But for turbulent kinetic energy, it's obviously seen that the K omega model in the blue dashed line failed to predict the turbulent kinetic energy in the deceleration stage, where the stress omega model compares very well with experiments. And here are the Reynolds stresses. Actually, two-equation model can also manage to estimate the Reynolds stress components, but not physically correct. So we can see here the stress omega model generally matches very well with experiments. The only discrepancies at the tau 11 in the deceleration stage, where the stress omega model slightly underestimates the Reynolds stress tau 11 component. But generally, it is able to see that the RSM stress omega model is much superior compared to two-equation models in simulating oscillatory with boundary layer flows. So now we are quite comfortable to apply our RSM models to simulate breaking waves. Here is the case for spilling breaker. The snapshots of turbulence level nu-t over nu shows that before breaking, there is no pollution of turbulence. So the turbulent kinetic energy before in the potential flow region is almost 0, which is quite similar to the performance of the stabilized two-equation models. And for the surface elevation envelopes, the simulation results by stress omega model shows an unprecedented accuracy we have ever seen based on our previous study using two equation models. This comparison is extremely well, especially for the breaking point, which is almost identical to the experiment. And the gray shaded area is the plus and minus one standard deviation. And we are further happy to see that the Wilcox stress omega RSM model predicted the undertow velocity profile very well, both from pre-braking, where x equal to 5.945, to outer surf zone after braking, where x equal to 7.885, and further closer to the shoreline in the inner surf zone at two locations, x equal to 9.11 and 9.725. The Wilcox stress omega model predicted very well from pre-braking all the way to the inner surf zone for simulating the undertow profiles. And here is the case for plunging breaker. The snapshot of turbulence level demonstrates a similar feature to the spilling breaker one, with no pollution of the turbulence level before braking. And again, the surface elevation envelopes matches very well with experiments. And since Larsen and Furman did not simulate the plunging breaker in their study, we only compare our results with the experimental data. And again, it shows that the undertow velocity profile matches very well with experiments from before braking all the way to the inner surf zone. Here comes to the conclusion. The present study formally proved that RSMs are unconditionally stable in the potential flow region beneath surface waves. And comparing to two equation models, RSM have theoretical superiority, and they can predict accurate anisotropic Reynolds stress for simulating wave boundary layer flows. And the present study is believed to be the first proper application of RSMs to simulate breaking waves and demonstrate great improvements in the accuracy of undertow predictions, especially in the inner surf zone, which even stabilized two equation models fails to accurately predict. Here comes to the references, and thank you for the attention.